Hello, folks. Welcome to Rational Science. Unfortunately, today we're going to be talking about irrational science. Well, I'm still on the road. Long time now. Anyways, just so you know, we're going to be doing a little bit of analysis of what the mathematical establishment does. We're going to find out that not a single explanation, physical interpretation coming out of, Harvard, Cambridge, Oxford, Caltech, you name it, they are all irrational. Not one of them meets even the minimum criteria for rationality. So let's start here. We're going to start with a little history here. Let me very brief history of how science, or you could call it physics, developed. Many people equate physics with science. Okay, and here we have a little map and shows you what happened over the last 5,000 years. About 3,000 years BC, we had three regions, maybe Mesopotamia first, and followed by Egypt, and then maybe India around the same time. We don't have exact dates, but around 3,000, maybe even up to 4,000 years ago, you had these regions where they started doing measurements and creating some kind of quantification system in one way or another. I didn't include China because there's not that much information for China. The farthest I could go with 1,000 or like 1100 BC. I'm sure there's more out there, but the point here is that maybe 3,000 years BC, that's when we started measuring the land, and that's when geometry came into being. And geometry is the first step in uniting math with phys, right? We have mathematical physics because you have the physical part, which is the object, the solid, and you have the math part, which is the measurement and the relation of how big something is with respect to something else. So that's where it started, more or less. About 800 BC, the center of the world, of the scientific world, moved to Greece, and obviously the Ionian Islands and some of their colonies there in that whole region of around Greece. And 1,600 years later, about 800 AD, we start with the Ottoman Empire, what they did was they took some of the stuff from the Greeks and they developed it a little further. A lot of it was just technology that they developed, but they developed some new concepts and so on. And eventually we reach Europe really around the 1500s. You have Italy and Spain, and then around the 1600s where they made most of the advances or the changes. We have this scientific revolution, primarily in France, Germany, and England. Okay, so that's more or less how science moved over the centuries. Okay, so from there you can say that we ended up in the 19th century, again, primarily in Europe, with people developing notions of what light is specifically, electromagnetism. They discovered electricity. They played around with magnets, try to figure out what this thingy called field is. And eventually we stopped doing what is known as classical physics, classical mechanics, and we ended up with the nonsense we have today, which is quantum mechanics and general relativity, followed by bigger nonsense still, which is string theory. So all we have today is nonsense. And we're going to see that is the case, exactly like that. Okay, so what is nonsense? What is irrationality? Let's start there so we have a definition we can all sink our teeth into. Here it is. Irrational is deprived of reason, and reason is a basis for or cause. That's according to the dictionary, okay? And I mean, that's not very clear, but you get an idea of what we, in general, what we mean by irrationality. But we like to define it a little more specific for physics, okay, science. If you attempt to move a concept, your theory is irrational. We cannot move concepts, okay? You can only move objects. So all those people who talk about the ether, field, plasma, energy, mass, time. You can't move those things because they are not things, okay? And so anyone trying to move or in any way modify, vibrate, bend, etc., any of those concepts, that's irrational. That's an irrational theory, because you should be able to use words such as bend and move and orbit or whatever. You should be able to apply it only to objects. That's starting point. You can't. That's non-negotiable. Then you have inconsistent definitions. First of all, people don't define. Nobody has learned how to define words scientifically in the last 10,000 years. So we don't have scientific definitions, and we do harp on scientific definitions here because if you're going to communicate ideas, we need to know precisely what you're saying. Otherwise, different people interpret different things, and we're all lost. We're debating in circles. This guy thinks this and says that, and the other guy thinks something else and comes, with a wrong answer to the wrong question, and so on. Now, you need to have definitions. They have to be consistent. If they're consistent, they're rational. If they're used consistently, they're rational. They're scientific. If they can't be used consistently, like the words energy or mass, there's 7 definitions for mass. Field, we don't know what a field is. It's defined as a bunch of numbers, and they start saying we're going to vibrate them. You can't do that in physics, not in science. Okay, so that stuff does not belong in science. That language does not belong in science. And then you have unimaginable objects, mechanisms. They have this object called 4-dimensional space-time, and they say we cannot imagine it. Okay, so what am I supposed to be imagining, visualizing when you talk about space-time? And space-time's the easy one. They talk about 10-dimensional objects, 11-dimensional objects, 26-dimensional objects in string theory, and that's beyond any hope. Okay, so no, there's only 3 dimensions. It's length, width, and height. And those are the only ones we can conceptualize having direction at 90 degrees to other directions. Period. We're done. That's it. Anything beyond that is irrational. So anyone who talks about 4D and above or less than 2D, they talk about 1-dimensional objects, 0-dimensional objects. No, I cannot imagine that, really. I'm not that smart, okay? And then the theory doesn't follow from the assumptions. And I use a very simple example. The prosecutor presents a knife at the beginning of his case, presenting his case, and then talks about, the person being shot or poisoned or whatever. No, it's got to follow from the assumptions. If you're going to make the assumption that the murder weapon was a knife, hopefully the theory says something about stabbing, okay, that sort of thing, okay? And so we have to be consistent in other words, the theory has to follow from the assumptions. So all these are what we call irrational. Anyone that doesn't follow those guidelines is proposing an irrational theory. That's the way we look at it. Okay, so here we have some strategic irrationalities that plague what we call mainstream mathematical physics, right? And here you have a listing of them. The definition of object. No one has ever defined what the word object means. And they do have some definitions out there, but they're all irrational. They talk about the see-touch criteria, that you have to see an object, you have to touch an object, and those two are irrational. Why are they irrational? Because in order to see, you need another object. In order to touch, you need a second object. In other words, to define the word object, you're invoking already another object. You're invoking 2 objects. They have to touch each other. The asteroid has to hit the moon for both of them to become objects, meaning that before they touched each other, they were not objects. An asteroid standing all alone in the universe, that's not an object according to these definitions. And then, there's another one which says that an object is what it's made of, made of a bunch of objects. No, that's also irrational, because you can't say an object is what is made of many objects, okay? And they use that for the particle, especially definition. Then you have the definition of exist. Why are these 2 definitions important? Why? Because Physics is a discipline that cannot be done without objects. You need objects to do physics. If God comes in there and wipes all objects from the universe, you have absolutely nothing. What is happening? What is taking place? What are you seeing? What are you measuring? What are you analyzing? So this is the issue. And then you have the definition of exist, the same. Exist is in other words, physics is the science of existence. Okay, if you do not define the word exist, you do not have any physics. That's how simple it is. Physics is the science of existence. Physics tries to elucidate what exists out there, especially those invisible, intangible objects, right? And with them, try to explain how the universe works. So you do absolutely need the word object and the word exist. One of the reasons theists, atheists, and agnostics go around in circles is that they never define the word exist. And they say, well, yeah, let me look at the dictionary. And that's the worst place to find a scientific definition. You will not find a single definition in any dictionary on planet Earth. Okay, so don't look it up because it's going to be irrational. Why is exist irrational? Because they're using synonyms. They're saying, well, it's to be, or living, or reality, or what's real. And you look up those words and they say they're defined on the basis of exist. So no, exist you cannot define, or object you cannot define on the basis of synonyms or antonyms. You can say an object is what it's not. That's not a definition. That's a synonym, an antonym turned into a synonym, right? That's what it is. Okay, ether as an assumption. That's been a plague throughout thousands of years now. No, we do not use the ether. Ether is a bunch of particles. That's all it is. It's this unknown out there, a bunch of particles that form some kind of background, okay? And some of them have it waving, some of them have it vibrating, others want to make it stand still. Others equate it with space, say space and ether are the same things. Others say that space is like a container and ether fills it, and there's no place in space that's not filled by the ether. And they have all these different notions because no one has defined the ether. And so we get rid of the ether totally because it's a word that only confuses, that muddles the conversation. We don't use the word ether. Ether is what space-time is. Ether is what the false vacuum of quantum mechanics is. All of them are ethers. That's why we get rid of all of them, because it's a bunch of particles. That's all ether means. And when people say, no, Bill, you got it wrong, you don't know what ether is. Okay, tell me what it is. In fact, don't tell me. I don't want you to tell me what the ether is. Because if you define it, it's a concept. And you're not going to tell me that you're going to move a concept later on, because now you're doing it in irrationality. You have to point to it. Okay, that's the ether. You got to show me some kind of image. Okay, so you can point to an image, I don't know, in Google or some site that's out there, or your own. I mean, just show me a picture of your ether. Then we can use it as an object, as a thing. Otherwise, it's a concept, and concepts do not move. You cannot use them as a thing that serves for your theory, like you're going to be shaking the ether, vibrating the ether, moving it from here to there. So ether has been a plague throughout centuries, and again, space-time is ether. That false vacuum that used in quantum mechanics and all these vacuums that they have out there with different levels of vacuum, they're all ethers because they don't know what they're talking about. Vacuum is not a thing. You cannot say the vacuum does this, like shoots a virtual particle into the real world. That's all nonsense. You have to start by showing me your vacuum first, then, if you're going to talk about particles coming in from the vacuum. Okay? In other words, creating something out of nothing. Similar to that, space has been treated as a thing for the last 10,000 years by at least, I would say, 90% of the people out there. No, space is the opposite of things. Space is nothing. Nothing. Absolutely nothing. What is nothing? That which has no shape. If an object is that which has shape, nothing is that which doesn't have shape. So we have something and nothing. They are antonyms. Now we can use them consistently. We can talk about somethings and nothings, okay? And again, the fact that you use it as a noun in an ordinary sentence doesn't make the word space a thing, okay? It's a noun, it's a the subject of the sentence, but it's not a thing. Okay, the other problem, again, mathematical physics is totally irrational because it uses concepts as mediators. That's the big problem. Field, plasma, ether, time, mass, none of those, energy, none of those are things. You cannot use them as things. And they've gotten so used to these words that they introduce them into their physical interpretations. And you cannot do that. Not if you're going to explain a mechanism. You need to have a thing, and none of those words qualify as things. They are all concepts. Concepts cannot be used as objects. He who does use them in their dissertation is doing irrationality. Creationism. Everybody thinks that there's been a beginning and there's probably going to be an end. And that comes all the way to the days of biblical days and even before then. Everybody thought the universe had some kind of beginning. And of course, you needed the guy with a magic wand, and that was God. So he created the universe from absolutely nothing. Now, creationism never happened. There is no origin to the universe. There will be no end to the universe as mathematical physics holds today. There was no starting point, no ending point. Okay? There's a single thread in all of space. That's the proposal here. And that turns into every atom and the interconnections that bind them all. And that's been there forever and will be there forever when we're gone. Big problem in mathematical physics, every cosmic phenomenon is done with mass, gravity. It's all gravity. There's nothing else. That's all they touch upon. Mass and gravity and mass. And so what is dark matter? Well, it's some kind of mass energy. What is what is a black hole? Mass energy. That's what they talk about. And no, you can't do everything with mass. There's something else called electromagnetism, right? Another type of, we'll call it force, right, out there. And they don't use that at all. That's the funny part. They don't use electromagnetism at all. Okay, so that's the introduction. Let's see what we have for each one of the branches. We're only going to touch today upon quantum mechanics and later on general relativity. So here's a rundown of what we're going to be covering in quantum, the hypotheses and theories which are irrational. An object, see, touch, again, that's irrational. An object that is what it is made of, right? Those two definitions are irrational. You cannot use those in science. So those are the ones that people use today, primarily the first one there. And of course, if you take like the black hole, you can't see or touch it, and it's not made of anything because it crushed all matter out of existence. So it doesn't meet either one of those two definitions. It's still considered an object. They talk about it being an object. And sometimes they even put the adjective in front of it. It's a mathematical object, whatever that is. I don't know what a mathematical object is. Okay, so we have first this particle is not a particle. That's a big one today. They talk about particle accelerators, particle physicists. They accelerate particles. What is a particle? And when you look it up, this is a big one here, okay? Because this is what it says. Particle or corpuscle in older texts, obviously wrong because a corpuscle is not the particle of quantum, by the way, is a small object. That's how it's defined. Small object. And you look up object and it says it's a collection of matter. What is matter? A bunch of objects. So we have, what is an object? A collection of objects. That's the definition they have. It says which can be described. They're going to describe it. They're going to describe it. They're not going to define. They're going to describe it by several physical or chemical properties such as volume, density, or mass. So they're talking about mathematical concepts. Volume, density, and mass have nothing to do with what an object is. Okay, so the fact that you can describe it or not through these mathematical concepts is irrelevant. We don't care about that. Okay, it says the term particle is usually applied differently to three classes of sizes. So now it's a question of how many sizes they have. In fact, it says before that the term particle is rather general in meaning and is refined as needed by various scientific fields. So everybody has a different definition of what an object is, of what a thing is, okay? And that already gives you an idea. We have a problem. It's like they have all these different notions of what an object is, and take whichever one you want. So I don't know, if you're in medicine and you think an object is this, the guy's talking physics and you're thinking of your specialty, your discipline, saying, oh, I know what he's talking about, when you absolutely don't know what he's talking about. He's referring to a word such as object, and you have a different notion what an object is. He's got another one. You're not communicating, period. It's just that simple. And again, says the term particle is usually applied to different classes of sizes. And you have the macro, essentially. You know, there's a couple subheadings there, but we have the macro world, anything above an atom. Okay, so those are objects that usually we can see or touch. Not totally true. You can't see the air. Okay, and certainly you cannot touch the table on the other side of the earth. Right? Right now you can't touch it. So is the table not an object until you touch it, until you go to China and touch the table the China man has over there? So we got a problem with that definition, that notion. Then you have the subatomic world, anything under the atom. And eventually you reach what is known as the point particle. And that's the killer one, which says it lacks spatial extension. So we have a point particle is that which lacks spatial extension, and what they do, that's the one they're going to use in quantum mechanics, that last one, the point particle. So everything's a point particle. Electron is a point particle, muon is a point particle. They're all point particles. And the funny part about that is they're all also elementary particles. They're fundamental particles. What's an elementary or fundamental particle? One that is not made of other parts, of simpler parts, that has constituents. And they take the pion, they say, what's made out of muons? And both of them are elementary particles. What's a muon made of? It's made out of electrons, because once you break it up, you end up with an electron and some other garbage out there, some residue. And so how can they all be elementary particles if one is made of the other? So they have all these contradictions. They just plow over them. They don't care. They don't even pay attention to their definitions. And that's the big problem, because then you don't know what they're talking about eventually. Okay, the next one is that they have this irrationality in quantum that a particle can be at two places at once. I want you to think about that for a second, okay? Does that make any sense to you right off the bat, intuitively? I mean, a particle being at two places at once. It's like, your cat is at two places at once. Is that possible? How can a particle be at two places at once? What sense does that make? If two particles are at the same place, we might be able to think about it. You're seeing a single particle and you're saying it has two different states. That's the way they put it. Okay, fine. That's stretching the imagination. But a particle being at two places at once, two locations, please try to translate for me that one. I don't understand it at all. And you say, Bill, you're pulling stuff out of nowhere. No, here I'm going to put some authority here, okay? So you see it. This is on Science, right, the magazine. One of quantum physics' greatest paradoxes may have lost its leading explanation. It says, it's one of the oldest tenets of quantum theory. A particle can be in two places at once. Okay, textbooks state that the act of observing the particle collapses it. So don't observe them, because you're going to collapse the particles. You observe your table, it's going to collapse the wave function of the electron or the proton or whatever that makes up the table. And I suppose that your table collapses or disappears, I don't know, such that it appears at random in only one of its two locations. So it's at two locations or many locations. When you look at it, now it goes to one location because you looked at it. This is the nonsense that comes out of mathematical physics. A particle is made to be both here and there. These are the statements that these people make. And you might say, well, Bill, you don't have to take it literally. Should I? I mean, I thought physics was literal. I mean, you can use an analogy. You can say, my table is as hard as a tree. We can all understand that. But when you say that, a particle, when you look at it, it appears, it comes from all its locations and suddenly collapses into a point. This wave function, whatever a wave function is, it's spread out throughout the entire universe. And just because you look at the table, that wave function collapses to a point, to the atom, the electron, the proton, whatever, neutron, and now it becomes something that you can see or touch or measure or whatever. Meaning that they put the observer at the center of other theories. That's dangerous because that's opinionated. That means they're not going to have something objective out there. They say, well, it's not objective until you see it. Until then, it's subjective. It's flying around, it's vibrating, it's doing whatever. It's everywhere and nowhere. And then when you look at it, boom, comes all together into a point. Man, that's some magic. Okay, and but here you have, not that I'm pulling out of nowhere. Here you have New Scientist says the same thing. Antimatter is seen in two places at once, thanks to quantum experiment. A particle can be in two places at once, even if it is made of antimatter. Researchers have just performed an antimatter twist on a classical experiment used to show one of the foundational tenets of quantum mechanics, that all particles are also waves. Okay, so you have this notion that quantum mechanics has that a particle and a wave, that a light is both a particle and a wave, and an electron is both a particle and a wave. That way they cover all the bases. It's here and it's everywhere. It's both, here and everywhere. And it's only when you look at it that the wave collapses to a particle, and when you turn around, the particle goes back to being a wave. So, a particle can be on many places at once because they don't have a particle at that point. They have a wave, and it's a radial wave? It spreads throughout the whole universe. So it's not in one direction, it's everywhere, which contradicts the notion of the electromagnetic wave, the transverse wave. When they show you that, they don't show it going everywhere, like radially, like spherically. What they show is going in a single direction along an axis, and it vibrates or goes up and down or whatever along that axis. So we have these contradictions. That's why they can't illustrate what they're talking about. They simply cannot. It's impossible for them to do so. And you would say, well, that's a subatomic world. We can't see it. We don't know what's underneath. No. They've extrapolated this notion now to a bunch of atoms. They had to find jobs for all these people. And so they say, what do we do? Well, look to see if the wave function functions for many atoms. And so they have this. The same atoms exist in two places nearly 2 feet apart simultaneously. They're talking about atoms with S, okay? Quantum mechanics boasts all sorts of delightful odd features. There's a phenomenon called quantum superposition, okay? This principle of quantum mechanics suggests that particles can exist in two separate locations at once, okay? So I didn't invent this stuff, okay? Physicists from Stanford University? I didn't know they had physicists over there. Okay, have now demonstrated the superposition of a group of atoms. Now it's just one atom or a subatomic particle. Now we're talking about a group of atoms over a greater distance than ever before. And so they have them separated by more length than they had in the past, of more distance. Quantum superposition is made even more perplexing by the fact that it can only occur when the particles are unobserved. So please don't observe the particles, because then you won't see superposition. You got to, maybe, I don't know, I'm saying, what if we bring a blind man? Would that work? I mean, the guy's staring, but he can't see anything. Do you really have to see, or? I don't know. Okay, but forget about atoms. Now let's go into molecules. So, it's not only, they're getting bigger and bigger. Pretty soon your whole table is going to disappear as soon as you observe it. Okay, so it says giant molecules exist in two places at once in unprecedented quantum experiment. Giant molecules can be in two places at once thanks to quantum physics. Well, thank God, Every particle or group of particles in the universe is also a wave. Waves occupy multiple places in space at once, so any chunk of matter can also occupy two places at once. Okay, so that means your table can occupy two places at once, because now they're talking about chunks of matter. groups of atoms. We're not talking about a little subatomic particle. We're talking about molecules here, guys. Physicists call this phenomenon quantum superposition, and for decades they have demonstrated it using small particles. Okay, so now they've demonstrated, they proved it, right? But in recent years, physicists have scaled up their experiments, demonstrating quantum superposition using larger and larger particles. Now, in a paper published, blah, 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 an international team of researchers has caused molecules made up to 2,000 atoms to occupy two places at the same time. So now we're talking about lots of atoms, Now we're not talking about just a subatomic particle here, They're saying if we have a bunch of atoms, molecules, right? Because 2,000 atoms, now you're talking a lot of stuff here. Now you're talking about stuff that could be visible maybe by a scanning electron microscope or atomic force microscope or one of those. But forget about little atoms, forget about little molecules. Let's talk about objects. Here we have large objects, Need to be in two places at once? It may be possible. Quantum physics has demonstrated that tiny particles can exist in multiple places at once, but a new method may prove that it is possible for larger, visible objects to also exist in multiple places. Now we have Schrodinger's cat at two places, one alive, the other one dead. Quantum superposition, the quantum effect where particles exist concurrently in multiple places, has, historically speaking, only been thought to apply to tiny subatomic particles. But superposition of larger visible objects may in fact be possible. And so they have a paper there that they reference that proves it, that shows that it is within possibilities. Yeah, pretty soon they're going to say your desk is at two places at once, That's where they're headed, because this just keeps going on and on. At first it was subatomic particles. Now it's a whole your desk or your cat or whatever, your tree is a wave function, and as long as you're not looking at it, it's waving out there, throughout the whole universe. And when you turn around and look at it, now it collapses to a tree back again. Hopefully nobody looks at the trees that I got out there, because I need them all, because if I hope nobody watches them, because if they in the country it's said the other way around. I hope they watch them, because otherwise they're spread out throughout the universe. All the apples, everything's out throughout the universe. Many apples. Okay, but here we have you heard of Brian Greene, and he's got a different take on this. He says that it's not totally true that a particle can be at two places at once. That's the rabble version. That's for the masses, for the plebes out there. He's saying that really objects don't even have location to begin with. Electrons don't have location until you look at them. So he's got a different version of this. It's not that it's a wave function that is vibrating throughout the universe. It's that there is nothing there, and only when you look, that's when the electron suddenly collapses or appears. I don't know. I guess it's the wave function appearing, but he doesn't talk about wave function. He says the electron doesn't have location. That's what he says. So let's listen to good old Brian Greene here. Let's see what he has to say. Here it goes. Listen carefully to him.
The more precise way of thinking about quantum mechanics is there's simply no notion of the electron having a location, of occupying a position before you actually measure it.
So, what do you think? Now the electron doesn't have location. It's an object that exists but doesn't have location. And I thought that's what exist means, that it's an object that has location. So if it doesn't have location, it doesn't exist. And so I guess all the electrons that are making my camera here, my desk, etc., they don't have location until I look at them and suddenly they condense into an electron. I hope that's not the case with protons as well, because that would be protons, electrons, that's an atom. That means the atoms don't exist, don't have location until I look at them. That means my desk doesn't have location until I look at it. I'll let you figure all that out by yourself, okay? I mean, it's all total nonsense. these so-called explanations, physical interpretations, these mechanisms that quantum mechanics offers are total poppycock. Let's call it what it is. It's garbage. Okay, that's what it is. Okay, here we have another fellow. His name is Lawrence Kraut, and he's going to tell us something about spin. And the funny part here is that he says that some of these particles, like electrons, and maybe others as well, they spin in all directions simultaneously. Particles can spin in all different directions at the same time. I cannot even imagine that. I cannot imagine a particle in two places at once. Now they're saying that your top spins in a gazillion different directions at the same time. What sense does that make? And yeah, you won't hear it from me. Okay, let's make sure we get it from a so-called mathematical physicist. Here we have Larry Kraut.
Let's say I take two electrons and I create three-dimensional states that one is spin up and one is spin down. Actually, they have opposite spins. It turns out they're spinning in all directions at the same time.
It turns out they're spinning in all directions at the same time.
Is that possible? That your top spins in all directions at the same time? And I guess it was proven by these two fellows. His name is Niels Bohr and Wolfgang Pauli. And here they were looking at a top. And I guess that's how they proved it. The top was spinning in gazillion directions at the same time. Okay, so maybe that's where Larry Kraut got it from. Okay, and do we stop there? No, we have now this thing called entanglement. And this is what Einstein called action at a distance, meaning that there's this remote control effect where you press your button on your remote control and the TV turns on, and there's nothing between your remote control and the TV. Now we know that's nonsense. We know that there's something there. Okay, imagine if you were out in space, right? And you have a remote control that doesn't work, doesn't have any light. In fact, you don't have to go to outer space. Just break your remote control, point it at your TV, and see if you can turn it on. It doesn't work. So there was something there that was turning on the TV. Once you break your remote control, you can't turn your TV on anymore. So obviously something is coming out of there, because otherwise your TV wouldn't turn on. Okay, so let's hear Larry again. He talks about entanglement. He gives you a brief introduction of what they always prove in quantum mechanics. So here it is. Listen carefully.
So it is true, and this bothered Einstein, this spooky action at a distance. It is true that I can do what's called entanglement. I can entangle two particles like two electrons or two photons, creating them in a very special quantum mechanical state. Now I measure this one, and I find out it's spinning over here. It immediately makes this one spin that way. Immediately. It's instantaneous.
So it's not only that one object affects another one, but it does it instantaneously, he says, whatever he means by instantaneous. I guess he's saying zero time, and zero time is instantaneous, but that's just location. That's a static concept. It's in a single frame of the Universal movie. And so who knows what they mean by instantaneous? They would have to define that word very precisely in order to make their case. But, so we have action at a distance, voodoo, magic, witchcraft, whatever you want to call it. And we also have the fact that it's instantaneous. Okay, so keep those two in mind. Okay, and finally we have this many copies of you running around. Doesn't that sound irrational to you, the fact that there's another you somewhere out there in the universe right now? They say there's so much matter out there, so many atoms, that there's got to be another Earth And within that Earth, there's got to be another you, because there may be gazillions of Earths out there. And in one of them, we're going to find at least in one of them, we're going to find another you. This is kind of like previous lives, the fact that you come back to life after you die. It's kind of like that, because they're saying that there's two yous somewhere out there in the universe, maybe more than two yous, because they can stretch it out to say there's a gazillion yous. I never met another me. In fact, God forbid, Okay, so this is what it looks like, more or less. This is how they illustrate it. All these Earths out there. So that's the many worlds interpretation of quantum mechanics. Okay, that something happens here, but it branches out into all these different worlds. Okay, and it's more or less like the multiverse that you're gonna hear about in general relativity. That there are many worlds out there, and really the only reason they invented the many worlds and the multiverse and all this kind of stuff, alternative realities and whatnot, is so that they don't answer the question. They just leave it. They leave it with the question unanswered. You say, what happened here? And they say, well, in this world, in our world, in this Earth, right, in this part of the universe, you bought the lottery and you won you won the lottery, right? And the other one, someone killed you, and the other one, you robbed the bank. And so the next step is not guaranteed. That way they keep, your options open. There's no determinism. You have this free will. And in this one, you use your free will to rob a bank. Here, you used it to win the lottery. Here, you used it to shovel, snow off your lawn. So that way they keep their options open. They say they cannot predict what's going to happen next, and the way they do it with these many worlds. And so these are just irrational explanations because they cannot answer the question. That's what it is. And so they created these nonsense explanations, if you can call them explanations, all irrational. Okay, so now let's look at general relativity. What kind of nonsense do we have over there? Well, it's just as bad, okay? So here's the list, more or less. Again, these are impromptu lists off the top of my head. I'm sure there's a lot more for both categories, general relativity as well as quantum. Big Bang creationism. Everybody believes that the universe had a beginning. They talk about infinity sometimes. They talk about, God existing forever, but they cannot imagine that. They talk about it, but they really don't put anything behind it. Why would God be eternal? Who created God? Why would the world, the universe be eternal? Someone had to create matter. And the question is, how do you create matter? How do you create something from nothing? Okay? And this is more or less what you see out there. Okay, this is the glass with beer that fell sideways. Okay, and it starts here with the explosion called the Big Bang. Okay, so we have this great explosion, and this is what they teach people. They say there's this explosion, and all this matter is pushed outwards. And when you see it sideways, which is what you see here in the glass, right? All those lines that come down, those are time slices. And we're at the present, right at the farther right, okay? So they have this nonsense, and they say this is how the universe began, in an explosion. I mean, what are you staring at? You're staring at a hand grenade, okay? That's what it is, an explosion. And then many people tell you, well, it's not really an explosion. It was that the singularity started expanding. What's a singularity? Well, it's an infinity. And so they go on and on and on. They never put an object in front of your eyes. They put a little dot, but they say, well, don't think of it as a dot. Don't think of it as a ball. You have to think of that little dot, right? The one that's going to explode there. Okay, you got to think of that as really a concept. Okay, it's what it is. You're staring at a singularity. And what is a singularity in terms of Big Bang? What means that if you take all the matter back in time, right? Yesterday, the day before, and so on backwards in time, right? So to speak. you're going to arrive at a point where all this matter was all crunched together into a little ball. But it turns out that some treat it as a little ball, and others clarify for you, the mathematicians clarify for you, it's not really a little ball. What it is all this matter is forever and ever and ever and ever coming closer and closer and closer and closer to each other, but never touching, never making that little final dot. So it's like no matter where you cut the movie, right, you're always going to end up with a little circle. And all the matter is in that circumference, or if it's a 3D, obviously 3D, in that sphere. Okay, so it's a sphere that's becoming smaller and smaller and smaller, but never reaches zero. It never reaches a point where it all disappears or turns into a little solid ball. It's just falling forever, approaching zero, but never reaching zero. And that's known as a singularity because it's a mathematical concept. So the universe started with a mathematical concept known as a singularity. Now you know, okay? That's what it is. Then we have space-time, the canvas. They have this space-time thingy, which is not a thingy. And a fella called it in reverse. I like that. I think it's better to call it time-space. Because if you call it time-space, it hits you in the ear a little more, and then it maybe wakes you up, out of your hypnotism, right? Time-space is better. But what is it? What are we talking about? Are we talking about canvas? Are we talking about a fishnet? No, we're talking about something else. We're talking about number lines. That's what they are, okay? And so here, this fellow, Brian Greene, he talks about this. He says, we're talking about time as being one of the dimensions. When it's not, it's a number line. And they have these number lines which they warp. They bend them and do all kinds of things with them. But it starts with time. That's where all this stuff started. And here, let Brian Greene tell you a little bit about time. Okay, here we have this time thingy, okay? And what he's going to say, he's going to cut it into slices. He's going to, you saw this space-time glass that was turned over, fall on its side horizontal. And he's going to cut it into slices, but he's going to say something that is shocking. He's going to say that your now is not my now. You have a different now than my now. Okay? Because there's a time delay between the time you see me and I see you. So if I'm traveling at a given speed and you're traveling in the other direction at a different speed, well, you're going to measure my time differently than I measure your time. And because we measure our times differently, we don't know what now is. There is no such thing as now, according to Brian Greene. So let's hear it from the horse's mouth. Here he is. Okay, give me a second here. I don't have I have not put the words underneath on this one. I didn't have time, but take a look at what he says. Just listen to him. Okay, here goes.
Think of space-time as a loaf of bread. Einstein realized that just as there are different ways to cut a loaf of bread into individual slices, there are different ways to cut space-time into individual now slices. That is, because motion affects the passage of time, someone who's moving will have a different conception of what's happening right now. And so they'll cut the loaf into different now slices. Their slices will be at a different angle.
Okay? So what he's saying is, your now is in my future now. Because there's something with light there, which has to do with measurement or something, which we don't care about. And this violates the universal movie. So let's go with the universal movie so people know what this tool is about. It destroys his argument completely and all the arguments from general relativity. Here it is. This is the universal movie. What you see in a single frame of the universal movie. This is a 3D movie, by the way. I put it in 2D. I can't put it in 3D for you. Very illustratively with an image or whatever. So what you see in a single frame there is every atom in the universe. You can say that there's gazillions of atoms. Yeah, fine. We don't care how many atoms there are. We're not going to count them. We're saying that in a single frame, God took a 3D picture of all the matter in the universe. He put it in a single frame, okay? And the next frame, all those atoms moved to a new location. Every single atom in the universe moves to a new location. So what we see in a single frame is just every atom in the universe. And so the first problem is that you cannot have different nows, because that single frame that you see there, the one that's highlighted in the center, that contains every atom in the universe. And so there can't be a future frame at the same time as that one, okay, which is what he's saying, that if that's now, what is your now? You're saying your now is the one next to it. It can't be, because if that's true, then that means you're creating new matter at every single location, in every single frame. The previous objects did not disappear. And it's not that an atom moved to a new location, it's that the new location has the same atom duplicated, has a clone of it, and so on from frame to frame. So every frame you have new atoms. That's what they're saying, because that's the only way that your now can be different than mine and be in the future of my now. Okay, that means you're in the future of me, right? And your atoms are all there in the second frame, while I'm still in the first frame, and all the atoms exist in both frames. That means you created new atoms as we went along. There is no such thing as motion. What motion is in general relativity, according to this time nonsense that they have there, is that you're creating new atoms. Duplication. You're duplicating every atom. You're creating clones for every frame in a universal movie, which is total nonsense. That's what they're saying. Okay, so yeah, you can't use the notion that relativity has with time. There is no such thing as future, and there's no such thing as past. Father Universe only exists in the present. Every atom in the universe. That's Father Universe, space serving as background. And then every atom moves to a new location with respect to every atom in the universe. Therefore, I cannot go back in time to kill your grandfather or to meet Napoleon or Caesar, because if I can and Caesar is still there, those atoms did not change location. Those atoms stay there, and those same atoms are here today. That means that Caesar, he died, all the atoms are there, right? And you see the frames of his whole entire life, all these atoms were there, right? In every frame of the film that I want to cut, there's his atoms, right? 3D atoms, right? And I go back in time and I land there, and the atom is still there because it was never destroyed. It never moved to a new location. What was done is the next frame of the universal movie, a new atom of that atom was created. That's what they're saying. Total nonsense, total irrationality. And then you have, again, the space-time canvas there, right? Here it is. This is so dangerous, because this is what you see. This is the flat space-time. Looks like a board, but really it ain't. What you're staring at is number lines, okay? Because here, let's illustrate it correctly. This is with no object in the universe, right? This is nothing weighing it down. Okay, and what you're staring at is that. You're looking at numbers. Okay, so it's very misleading to say that space-time is a canvas. They illustrate it as a canvas, but what you're staring at are number lines. Okay, let's not confuse number lines with space-time with a canvas. Okay, space-time is not a canvas. They illustrate it as such, but it ain't. Okay, so just make sure you're aware of that. Okay, and so what do we do that with this? Well, let's illustrate this a little better so you can really sink your teeth into it. Here it is. Okay, so you have all these numbers, right? And what you're looking at is number lines called time, and they call one space. And that's a big monster there. There's no such thing as space number line, okay, or space dimension. Okay, what they've done is they've taken three dimensions, length, width, and height, and they illustrate all three of them with a single number line, because those are number lines, and they call it space. Okay, so language here is very, very important. Okay, so what they're doing is they're putting some number lines, putting these names, time and space, and people think they're looking at a canvas, a fishnet there, and it ain't. You're not staring at a fishnet. What you're looking at is a mathematical concept which they have illustrated. Much like I showed the other day with the transverse wave. What you're seeing is not a wave. What you're seeing is a bunch of vectors that form a field, couple fields, and those two fields supposedly are the transverse wave. And this is more or less the same thing. You're looking at a mathematical concept. Let's get that right, okay? And so what happens when you put a ball in there, on top of that number lines, right? We're going to weigh it down. We're going to bend the number lines here, fellas. Here it goes. See, that's what it looks like. They bend it. They bend the number lines. And this is totally ridiculous. I mean, this has no sense whatsoever. And, some of these people say, well, you shouldn't take it so literally. Well, I have to take it literally because this is how they're going to explain gravity. They're going to say, hey, we bend the number lines, and that's why the Earth doesn't fly out of the solar system. And here it is. Here's the illustration of that. Here, you'll see it. Okay, there you have it. This is what they illustrate. And so it's not like I'm putting words in their mouth and they're saying I'm taking it too literally. I have to take it literally because the moon doesn't fly away because there's a curved wall of warp time, warp space. There's a curved wall of space-time, time-space, that's preventing the moon from flying out. That means the moon is pushing up against a curved surface. It's touching it, because the moon is either rolling or sliding along that curvature, and that's why it doesn't fly out of the solar system. And the same with the Earth around the sun. So it's not like, the analogy. I want them to explain the analogy. If I'm not supposed to take it literally, for real, then what was the explanation? Why doesn't the moon fly out of the solar system? I need to understand the mechanism. And if the mechanism is that, the moon slides or rolls around space-time, well, I understand the analogy. But then they say, don't pay attention to the analogy. Okay, then what have I learned? What's the mechanism that general relativity proposes for gravity? And they do tell you that. They do tell you that mass weighs space-time downwards, and because it's distorted, it tells the mass how to move. So that is their explanation. That's the explanation of their equation, their field equation. And then they say, oh, but don't pay attention to any of that. Okay, I learned a lot today, Great. Okay, here we have the twin paradox, okay? How to kill your grandpa, is that rational? That you can go back in time, kill your grandpa, and then not be born? And they say, well, because of, these contradictions, they say you can't go to the past. You can only go to the future, okay? That means you can kill your grandson, but not your grandpa, okay? Okay. Sometimes I want to kill them. Yeah. Okay, so let good old Brian Greene explain to you how he's going to do this magic trick of going to the future. Listen carefully. Here it goes.
Is it possible to travel to the future or the past? But surprisingly, time travel might be possible. If you could travel to a black hole, the effect of gravity on time would be huge. And if someone watched you travel close to a black hole, they'd see time for you slow down dramatically. If I spend an hour or two in orbit, something like 50 years will have passed back on Earth. I will have traveled to Earth's future.
Okay, so now you know how to travel to the future. The funny part that I saw is that there was still a check-in agent in the future. That was scary. They still have check-in agents. Okay, so is this twin paradox worth anything? Well, again, this is all nonsense. You can travel at the speed of light. If you want to travel faster than light, no problem. I'll allow that as well. Travel faster than light, FTL. Right? To a black hole, to the other side of the universe, I don't care. Travel wherever you want and then come back. Hopefully, the number of times the Earth went around the sun is the same for both of us. So if the Earth went around the sun 50 times, we both should have 50 more years on our clocks. Now, if you take an atomic clock, there's no guarantee. Why? Because atomic clocks are notoriously inaccurate. And they've proven this many times by taking a clock, one of these atomic clocks, farther out. They did it with gravity probe A. They did it also with the, I can't remember the name of it now, but heating. Name doesn't come to mind right now. They took it on an airplane. They compared it against the twin clock that was on the ground, and they showed that they clocked things differently. And yeah, if you take the clock further out into space, you take it to Mars, you want to take it to Jupiter, it's going to clock, atomic clock, right? It's going to tick at a different rate. And so what have we learned? Atomic clocks are notoriously inaccurate. The most accurate clock to measure gravity is, again, a sand clock. In other words, an hourglass. You take an hourglass and you put it there, and little grains fall because of gravity. So it's the best clock to measure time. But you can't use it to go to another planet and come back. For that, you need the revolutions of the Earth. That's how we ended up with a second to begin with. We took the Earth, we chopped it into the orbit of the Earth, the revolution, and he chopped it up into little pieces, and they ended up with a second. That's how we originally came up with a second. Today they have a different measure. But the point here is that, the Earth goes around the sun, and there's no friction because you can't have friction. You can't rub your shoulder against space because space is nothing, meaning that which has no shape, right? So there's nothing there. And so the Earth goes around the sun without losing, a second. And that's the best clock there is. And so you have so many revolutions. You have 20 revolutions. Whether your twin brother goes out at the speed of light or even faster or slower, it doesn't really matter. When he comes back, hopefully we both counted 20 times, for the Earth around the sun. And that's 20 years. And there's your clock. We should both be 20 years older. No change there whatsoever. Okay, and again, time slower, closer to the ground. Well, I proved the opposite. I proved that towards the ground, an hourglass goes faster. But this is what Brian Greene tells us about the hourglass. Okay, listen carefully. Here goes.
Compared to someone living on the top floor of a skyscraper, someone living on the bottom experiences time elapsing a little slower because gravity is just a tiny bit stronger closer to the ground.
So not true, because an hourglass ticks faster the closer it is to the ground, and that is a gravitational clock. So again, this notion that they have that clocks tick faster here and slower there, well, you got to get it right. You got to use the right clock. And the gravitational clock, the best one to measure gravity, is an hourglass. Okay, so keep in mind when you do the experiment, do it with an hourglass. Here's another fellow, and he's going to tell us about what number of atoms increases with speed. And they have all these things, the sticks shrink by magic. In other words, they have this not only time dilation, but they have mass increase and length contraction. And they say when you travel at the speed of light, or close to the speed of light, your mass increases. Well, how can that be? Mass is the quantity of matter. So why does the quantity of matter in your body or in whatever object you have, why would it increase? Why would you have more atoms? Because you travel at the speed of light, or close to the speed of light. Why do you bloat? Because if you bloated, it means that more atoms came into you, because that's what mass is. It's defined as the quantity of matter. Okay? And so we have a contradiction, because they say because you travel at or close to the speed of light, your mass increases, but they don't have a mechanism for it. It's just math. They just calculate. And so that can't be, unless they're talking about weight, meaning that you press against a scale, and so you weigh more. That's weight, not mass. But if you're going to talk about mass, you're talking about quantity of matter. Okay, and so here, let the guy from the Fermi lab tell you this. Okay, Fermi lab, that's where they do acceleration of particles which ain't particles. And he's somewhat popular. His name is Don Lincoln. Here he goes. Okay, listen carefully to him.
Without a doubt,
Albert Einstein's theory of special relativity makes some very mind-blowing predictions. Clocks run at different rates, objects shrink, and things can't go faster than light. And all of these things are absolutely true. Relativity has been thoroughly tested, and there is no credible criticism of the theory.
So the good thing is that they've proven it. It's proof, evidence. You can't challenge it anymore. They've proven it. And so, yeah, all I can say is, how did the mass increase unless you added more atoms, meaning more matter? And where's the mechanism? Well, they say mathematically we proved it, and it sounds like they're talking about weight, how much something presses against a scale. Of course, if you push with your hand against the scale, your bathroom scale, it's not the same thing as throwing an elephant, or just put the elephant just standing there, right? It's going to have a certain weight. Now drop the elephant on top of the scale. That's got to go, it's got to go very much higher because now you're talking about weight. The elephant did not increase in weight, in mass. The elephant just increased in speed, and that's pressure on the scale. And that's called weight. It's not called mass. The elephant did not gain matter when it fell. So it's very simple to overthrow the nonsense they have. And the issue is, again, they have all these different definitions of mass, and one of them is a synonym of weight, and that's the one they throw in there, and they say, well, it's relativistic mass. No, relativistic mass is just weight. It means the thing is traveling faster. It's got nothing to do with quantity of matter. That's where the problem is. Okay, and then they have all these other, same with a shrinking stick, by the way. Why would it shrink? What's the mechanism? Don't tell me my stick shrunk, and it only shrunk. It didn't shrink in my proper frame of reference where I'm at. It shrunk from the other guy's point of view. Okay, so it's a optical illusion. The stick did not shrink. Okay, I measured my stick to be 1 meter, and I always measure it to be 1 meter. If the other guy measures it to be a little longer, a little shorter, that's his problem. He's got maybe a problem with astigmatism or who knows. It's got nothing to do with physics, with the reality of what's out there. Okay. They have these dark spirits. They have black holes, dark matter, dark energy. Let's see what that's all about. Here we have a star, and it collapses. Okay. What does it collapse to? They say to a point. What's that point? It's a black hole. Okay. So a star collapses and disappears from sight, essentially. But they say there's something there. The elephant's gone, but the weight or the mass, right, that the elephant had is still there. And so it causes havoc to anything in the vicinity. Even in vicinity could be gazillions of light years away. They have to show how that black hole, as they call it, can affect something very far away. But even if we concede that, even if we were to concede that, how does it do it? What is the physical mechanism? How does that little thing there affect a star that is, 1 light year away, for example? And they can't. And so this is the black hole. This is what it looks like. This is what a black hole really is. Okay, these are the pieces of a black hole. And you can see what it has. It's got a singularity at the center. What's a singularity? Well, again, take your pick. It could be a little ball, right? Right at the center. That ball has 0 dimensions, 0 volume, 0 everything. There's nothing there. It's got no shape. Okay? That's one notion that people have out there. All matter is crushed out of existence. There is no matter within that radius, the circumference there, right? And that's one notion. The other one is the singularity is really something else. It's runaway math. It's infinity. Matter is approaching the singularity, but never reaches. And so the question is, how do they have these spaghettification, where they say that if you survive spaghettification, you go through the little hole and end up in another universe? Well, hold it. I thought you said we never reached the singularity. But then they have you go into another universe through a wormhole, through that little tiny zero-dimensional hole, whatever that is. So it's all poppycock. It's all nonsense, garbage. None of this survives rationality. You cannot say that what they said is rational. And again, the event horizon is again like the campfire. think of black hole as a campfire, the center, the singularity, right? Think of it as a campfire, and event horizon is like the heat. Okay, how far does the heat from the campfire go? Well, let's say 2 meters or whatever, 3 meters. It doesn't matter, right? Well, that's the event horizon. It's the region of influence of that campfire in the center. That's essentially the notion of an event horizon. And so we have a singularity, which is absolutely nothing. It's a zero-dimensional ball or infinity where matter is falling, 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 and never reaching the singularity, except you who can make it through the little hole and go to another universe. And that nothingness there, that zero-dimensional whatever, singularity, right, has so much mass that it creates this event horizon, its region of influence. And anything within that region, if you pass through there, well, then you cannot escape because no matter can escape at the velocity of light. No matter can travel at the speed of light. Okay? And so, these are the little theories that these people have. Take them or leave them. I don't know what to tell you. This is all nonsense. This is poppycock. This is what's coming out of respectable places like Cambridge and Harvard, right? So keep that in mind. This is official. This is what you're paying for because a lot of your money, from your tax goes to these places, and they pay the so-called mathematical physicists, right, to do all this work, to do all these calculations. Then they come back and they give you this irrational explanation. They have no idea how this universe works in quantum and in general relativity, in the micro world and in the macro world. They have no clue whatsoever. And of course, the famous wormhole. Here's the wormhole. Okay, if you've never seen one, let's look at it. Here it is. That's a wormhole. And what you're staring at, you might say, Bill, you're kidding me, is 3D, 2D. No, it's 1D. It's one-dimensional what you're staring at. It doesn't look one-dimensional. In fact, it would look like it's a three-dimensional whatever on a two-dimensional background. That's what it is. There's no one-dimensional anything in what I'm staring at. That's your wormhole. And supposedly it's what takes you to another universe. So I don't know what to tell you. These are the nonsensical things that they illustrate. And you say, well, maybe math cannot be illustrated. Well, if that's the case, like, you have some people, Sabine Hossenfelder and some of these other so-called mathematical physicists, right? And they tell you, well, really math should stay with math because we cannot really put in ordinary language, in ordinary speech, our math, our calculations, our notions, our concepts that we have in math. Well, then that means math is not the language of physics because physics is physical interpretations, causes, mechanisms. I need to see something. I need to see what the mechanism is. They don't have a mechanism for anything. And so the question is math the language of physics? And the answer is a resounding no. Okay, it's not. We don't use math and physics. What we use is objects. You have to have an object. If you have an object, then you can put it in motion. You can show a mechanism, and that's physics. But to say that you did some math and you tell me how something moved, and that something is not a something, it's a concept which is a nothing, then we have a problem. Because now you can't give me a physical interpretation, which is the physics part of mathematical physics. Okay, so that's where the problem is. They're not doing physics, but they claim to do. They call what they do physics. Okay, and then here we have, just in case, we have this, which is the funny part because they have this dark matter, dark energy, which is 96% of what they don't know about the universe, and the matter that they are aware of is only a 0.4%. They have 3.6 non-luminous, 23% dark matter, 73 dark energy, and that tiny part, the 0.4, is what we see. What we can see, what we can measure, that kind of thing. And the funny part is when they say that that's a measure of their ignorance. In a way, I do agree, but no, they even got that wrong, because the fact that 99% of the universe is they don't know what's out there is not a measure of ignorance. Ignorance is, if you have 99% ignorance is when you're a mathematical physicist. Then you have 99% ignorance. But you cannot say that because all this dark stuff out there that you don't know anything about is a measure of your knowledge. No, it doesn't follow, but this is how they put it. Anyways, you can see there that this is how they break it up. They're looking for this stuff. A lot of money is going into dark matter research and dark energy research. And they say, hey, we got job security because, 99% of the stuff we know nothing about. And so they got a lot of money there for research, right? They can research this forever. What they're researching, they're doing, inventing math. That's all they're doing. And finally we have the multiverse, okay? Just like we had the many worlds in this, in the general relativity world, they created the multiverse, meaning there's a bunch of universes, and where every step you take, you end up with a different, a different place. And again, a lot of this stuff has to do with rebirth, right? The fact that you come back from the dead. So, these are not new concepts. They've just introduced all this stuff, into physics, into science. They just took it from these religions like Buddhism, Hinduism. They say you're going to be reborn, etc., and then you come back in your next life and whatever. And that's what all this is about. It's a way of introducing religion in the guise of science. They just took these same ideas, put them in there, and we're done. And that's how they explain these things. Okay, so what's the bottom line? Well, I have a little corollary for you. Let me take this one out of here. Here's the corollary to all this. And this is it. The most astounding failure of mathematical physics, right, which testifies to its irrationality, is that in the last 5,000 years, really more, right, mathematicians have been unable to discover what causes a spoon to fall to the floor. Here I have a spoon, right? I let go of it. Very simple experiment, very simple experience that everybody has gone through in their life. Something falls from your hand, falls to the floor. Little spoon, right? Plastic spoon falls to the floor, right? And they cannot explain the simple phenomenon. And then I think that shows how much mathematical physics is really worth. They cannot explain something as simple as that. And all they had to do all these years was, identify the invisible objects that come in physical contact with a pen, with the spoon. Because the issue here is that this would not fall if something were not pushing or pulling on it. Something is in contact with every atom of this spoon. So, because if we have it in outer space where there's, no physical object close by, it doesn't really fall. Well, it just stands there, kind of maybe floats around, who knows. But for it to fall, it's got to have something in contact with it, and you have to have the Earth, a moon, some object, some planet, some big object, right? And then something from that object must be touching the spoon for it to move downwards towards that object. And for you to say that there's nothing there or nothing here, nothing at all here because you can't see or touch it, that's where the error is. And that's where we're at today. So for those of you who like mathematical physics, just keep listening to the authorities, and they're never going to tell you how this universe works. Okay, we'll see you next.